The indoor sound field is more complicated than the outdoor sound field. It sounds louder than the outdoor sound at the same distance from the sound source. After the sound source stops sounding, it does not disappear immediately like the outdoor sound field, but lasts for a period of time. These phenomena have a great impact on listening. In the outdoor sound field, the sound energy decays rapidly as the distance between the receiving point and the sound source increases. In the air without a reflective surface, that is a free sound field, the sound power of a point sound source is W, and it propagates outward in the form of spherical waves. The sound intensity is inversely proportional to the square of the distance, the so-called inverse square of distance law. From this, the calculation formula of the sound pressure level at a certain point in space can be deduced. From this, it can be seen that each time the distance from the point sound source increases by 1 times, the sound pressure level decreases by 6 dB. Attenuation is reduced by 3 dB in the presence of ground reflections. The sound pressure levels of the same sound source at different receiving points have the following relationship. The difference between the sound pressure levels at the two places is proportional to the logarithm of the ratio of their distance. The noise sound pressure level of products provided by manufacturers is usually measured in space without reflection and at a certain distance from the product. According to this relationship, the sound pressure level of the actual receiving point can be easily calculated without knowing the sound power of the sound source. Next, let's do an exercise. It is known that the noise sound pressure level of a vacuum cleaner at a distance of 1 meter from the vacuum cleaner in the non-reflection space is 80 dB. Find the noise sound pressure level at a distance of 4 meters under the same conditions. In this question, it is known that the distance between the two receiving points and the sound source are 1 meter and 4 meters respectively, and the sound pressure level at 1 meter is 80 dB. Substitute the relationship between the sound pressure levels of different receiving points of the same sound source and obtain 68 dB. Think about it. Can these formulas be used for indoor sound fields? Can this rule be used to estimate the listening effect of the room when designing a larger hall? Due to the reflection and absorption of the indoor sound field, the indoor sound field is different from the outdoor sound field. Therefore, the above formula cannot be simply applied. So how is the indoor sound field calculated? Let's analyze the indoor sound field first. The characteristics of the indoor sound field are: 1. The sound energy density of the receiving point is greater than that of the free sound field and does not attenuate with the square of the distance. 2. There is reverberation. Reverberation refers to the presence of late reflections from various interfaces in the sound field for a period of time after the sound source stops sounding. 3. Certain frequencies are boosted or attenuated due to resonance with the room. 4. Due to the shape of the room and the arrangement of decorative materials, there may be phenomena such as echoes. Therefore, the indoor acoustic design needs to control the shape of the room and the distribution of sound absorption and reflection materials, so that the room has a good sound environment. Acoustics looks at the volatility of sound and can only address simple cases of simple size and low frequencies. Geometrical acoustics ignores the wave nature of sound and analyzes the propagation, reflection, and diffusion of sound energy in a geometrical way. The straight line perpendicular to the wavefront of the sound wave, that is the sound ray, is used as the propagation direction and path of the sound. The sound ray meets the reflecting surface to generate reflected sound. The reflected sound follows the principle that the incident angle is equal to the reflection angle. This figure gives 4 possible sound reflection situations in the room, and use symmetric sound rays to study the spatial distribution of reflected sound. A and B are both plane reflections. A is close to the sound source, and the incident angle changes greatly, causing the reflected sound to diverge. B is far away from the sound source, and the reflected sound is nearly parallel, so that the direction of the reflected sound is also close to the same. Both C and D are curved surfaces. The convex curved surface C diffuses the reflected sound, and the concave curved surface D focuses the reflected sound. Because the distribution of reflected sound in space and time has a greater influence on the sound quality, and multiple reflections will make the reflection situation complicated, even close to random distribution. Therefore, the study of near-reflection sound is usually focused. You can use the method of geometric acoustics to try to analyze the spatial distribution of near-reflection sound for architectural design work, compare their path lengths, and test various surrounding rooms to see if there are acoustic problems.